Hello everybody and welcome to the first lab of Physics 2. My name is Jackson Lee. So as a brief introduction, the purpose of this lab is to examine the interactions between charged objects along with the effect of charge on electric force between the objects. And obviously the main principles we're looking at are gravitation, electric field, and relatedly electric force. The main results that we found are that the tapes which were positively charged possessed total charges of about 1.1 times 10 to the negative 8th coulombs. The initial conditions, there aren't many, but it's mainly that there's about a 0.026 meter height difference between the tape that was floating and the tape that was underneath it, and the mass was about 0.000165 kilograms. I should have included units there. So the system here is the upper tape that's being floated, and the surroundings are, of course, the Earth and the other tape, most notably exerting a charge on it. As we can see, we have the gravitational formula here, the electric field formula here, and the electric force, which you can rearrange this to get the electric force is just equal to the charge times the field. So the details of the experiment here. I'll just go through what we were told to write down. So since each tape was charged the same way, we would expect them to repel because they have the same charge. If it were positively charged, so it's known that there is a negative total charge on a pen that's been rubbed through the hair. So if the tape is positive, it should stick to it. If it's negative or neutral, it should repel. Yeah, if it's positive or neutral, it should stick to the pen. If it's negatively charged, it should repel, and it should attract very strongly if it's positive, not so strongly if it's neutral. And as it turns out, they were positively charged because the tape snapped straight to the pen. Since the tape was about a gram per meter, and because each tape was about 16.5 centimeters, we found that there was about 0.001617 newtons of gravitational force being exerted, and the distance at which it was floating was found to be around 0.026 meters. And setting the force of gravity equal to the electric force, with some fancy math that we'll get to later in the code, we see that the charge should be something like 1.1 times 10 to the negative 8th coulombs, very roughly. Going forwards, we have a bit more. Given that the number of electrons lost is equal to the positive charge divided by the elementary charge, the charge of one single electron, the total electron deficiency was about 6.888 times 10 to the 10th electrons. And so with a tape length of about 16.5 centimeters, as said before, and a width of about 1.7, we have a very small area, and once we multiply it by the width divide it by the width between the atoms, we get the number of atoms in the whole picture, which is about 2.8 times 10 to the 17th. And, doing a quick ratio trick, we see that there's about 4072356, whatever that number is, atoms for every electron that was lost. And these are the assumptions we made, basically that it was one atom thick, that we didn't dissipate any charge, and that the tapes were equal in charge. Also that the measurement was accurate. Here's my code. These were the assumptions that we were given. This one we did not assume. These two we did assume. You can pause this or click on the link to read my code further. And here are the results. So this is the real observed result, and this is the simulated result. Obviously, this was manipulated to be roughly equal to this. And so I'll tell you the charge in a moment once we get to the next slide. But notice this is really, really, really small, largely because our charge was much too small. It's a bit perplexing as to why, because there's a lot that could have gone wrong. But adjusting for it, we can see that we were about an order of magnitude off. So yeah, not so good. The charge that I used after estimating and, arbitrarily changing the number after a while was 4.25 times 10 to the negative 7th coulombs, and not the previous number. And this is probably due to a combination of the charges and masses being unequal between the tapes and unequally distributed, and the natural imprecision of measurement. And that's the one I think is really the problem here. I just think we didn't get a good measurement. We were using an old beat-up meter stick that someone was holding in the air. It was shaky. I don't have a whole lot of faith in the, strength of that measurement. I think we probably overshot it, and, if we had a much more accurate measuring tool and the tape were maybe less rigid, we would have gotten a better number. So the what if the polarity of charge between electrons and protons were reversed, we would just see the numbers reverse their polarity, like go from positive to negative or reverse, in terms of many of the vectors, like charge and electric field. But the overall values would stay the same. And what does it mean? By handling the charge tapes, we were dissipating some of the charge, therefore making our measurements weaker and unreliable, and that's what that did. But anyways, thank you very much. I hope you enjoyed.